Part 7 of Chapter 11 deals with quantitative risk analysis. Quantitative risk analysis often follows qualitative risk analysis, but both can be done together at the same time. Large complex projects involving leading-edge technologies often require extensive quantitative risk analysis. So the techniques that we will discuss in this part of Chapter 11 include decision tree analysis, simulation, and sensitivity analysis. By the way, I would say that all three techniques listed here, they're quite elaborate and they require quite a bit of theory, especially theory related to statistics, if you're talking about decision tree analysis or simulation analysis, or econometrics if you're talking about sensitivity analysis. In fact, one of my undergraduate courses is largely devoted to this sensitivity analysis. And then, of course, there are courses on Monte Carlo analysis, which is the main technique behind simulations. And then, I've seen quite a few books on decision tree analysis as well. So this will be an introduction, a very high-level overview of those three risk quantification techniques. So what is a decision tree? It's a diagramming, meaning visual analysis technique used to help select the best course of action in situations in which future outcomes are uncertain. One of the key concepts related to decision tree analysis is the so-called estimated monetary value. And it is the product of a risk event probability at the risk event's monetary value. So for example, if the probability of an event is 0.5 or 50%, and the monetary value of the event is $10,000, let's say if this event happens, it will bring you plus $10,000, then estimated monetary value becomes 0.5, which is probability times $10,000, and that equals to $5,000. It always helps to draw a decision tree to visualize the overall collection of events and associated probabilities. So a decision tree for two projects may look something like this. You have project 1 and project 2, and let's say for project 1 you have the following probabilities. Let's say probability of 80% involves an event where the project budget is completely approved. Let's say, to make it parallel to the numbers here. So let's say project 1 is a very risky project, so the probability of the complete budget being approved is only 20%. And the probability of, budget being severely reduced is 80%. So let's say if your budget is completely approved, then you'll get additional $300,000 to complete your project. If it's not approved, you will lose $32,000 somehow, right? And then you multiply those probabilities by outcomes and you get plus 60 minus 32,000. So the estimated monetary value for the entire project is 28,000. Okay. And for project 2, you have three outcomes, three different probabilities. There's a monetary value and the outcome is this. This can be done to model specific risk or the overall success rate of a project. So let's say, for project 2, we have the following probabilities. There's a probability of 20% that you will lose money, that the project will fail, and you will lose 50,000, 10% probability that you will lose 20,000, and 70% probability that you will succeed with your project and you will generate, let's say, 60,000 in additional revenues. By multiplying those probabilities by monetary values, you can get expected monetary value for the entire project. And then based on those estimations, based on those risk estimations and value estimations, you may decide to go with project 1, which has a higher probability. But again, this decision tree analysis can be more complex. There could be like branches, coming from the first level branches and so forth. And then there are those elaborate path techniques for doing all those calculations and trying to understand the probabilities, because if you have a probability here, then it becomes a probability that is dependent on this probability. So there are some rules, the so-called conditional probability. So there are the rules for calculating those conditional probabilities, and then formulas for estimating the entire monetary value of a particular project. Now, simulation, another popular technique for analyzing and dealing with risk. First, I'll give you some theory, and then I'll try to explain the practical essence of this method. Simulation uses as a representation or model of a system, and let's say in our case the system is our project, to analyze the expected behavior or performance of the entire system, and once again in our case the entire complex system is our project. One specific technique that is quite popular for simulation is a so-called Monte Carlo analysis technique. The keyword Monte Carlo is related to gambling. As you probably know, Monte Carlo is a small city-state. I think it's officially independent, but it's somehow related to Italy. It's it used to be a part of Italy or something like that. There are a lot of casinos there. A lot of athletes and celebrities live in Monte Carlo because there's a zero or virtually no tax. They use it like as a tax escape. So some of the celebrities, they give up their citizenship in Europe or somewhere else, and they move to Monte Carlo and become citizens there to avoid tax. And then of course some of the countries try to get them back, through court. Well, anyways, there are many casinos there. I guess those celebrities have so much money that they save from avoiding tax that they like to gamble. And Monte Carlo technique, it's something like that. You spin your roulette, and based on that spinning, you get certain probabilities, certain values of variables based on underlying probability distributions, and then you plug in those values into your model, and in our case it's the model of the project, and it gives you like some kind of numerical value. Just like in a casino, you play over and over again. You do this over and over again. You estimate those values of variables, you plug in those values, you generate output based on your model, and then you create a probability distribution for the entire project to have a better understanding of all the possibilities and their likelihood. Okay, so here we have those steps. I already explained to you, like in practical terms, how those steps work. So I'll just show you like how an outcome of a Monte Carlo simulation will look like. So imagine you're trying to predict the completion date of your project. So you're interested when exactly you will complete your project. Now, let's say your completion date depends on several variables. Let's say number of people working for you, that's variable 1, budget level, variable 2, top management support, variable 3, and so forth. And then based on all those variables that somehow impact your completion date, you create a model of your system, meaning a formula where you plug in all those values for variables and you generate a completion date. Okay. And then for each of the variables, you generate a probability distribution. And most of the time, statisticians say that most of the variables, they're normally distributed. They follow like a bell-shaped curve, okay? So based on those probabilities, you'll random pick up values for those variables, you'll plug it into the formula, and you'll generate a bunch of outcomes, a bunch of completion dates. And then based on those outcomes, you'll create a histogram. So right now, it looks like the most common, the most likely completion date. Now, those are the values you get the most, is around February 17th, right? So you see that's the highest probability rate because you get your model generates 50% of the time, your model indicates that based on the values of those other variables that you plug in, the completion date would be February 17th. So this is how it works. And then the outcome of the Monte Carlo simulation is this probability distribution for the completion date, and you can calculate standard deviation, mean, and stuff like that to create a probability-based estimate of the completion date. By the way, a lot of here you have some examples of companies being quite successful with Monte Carlo simulation. Indeed, I think it's a realistic method to think about future events. Nobody's smart enough to sit down and predict the future with cent or decimal precision. This is not how life works, right? It's hard to predict the future, especially when it comes to highly complex social systems such as organizations or IT projects. So instead of trying to predict it with 100% certainty, you just generate various predictions, right? Various plausible predictions, and you try to estimate how likely each of those predictions are. And just because you can calculate the average based on that, or expected value based on that distribution, does not mean that you will 100% subscribe to the idea that will be the completion date. You will see, okay, it will be somewhere around February 17, because we have high probabilities for other events as well, right? For other probabilities. Here, to be honest, I don't know what's happening. Why the probability is 50 and then 45? It just is it cumulative probability? Yeah, most likely. Yeah, so something is wrong because all probabilities need to add up to 1. So yeah, this is how it works, and you think about the future in a probabilistic sense, which seems to be more realistic than thinking that there is a model or formula that will give you like 100% precise estimate. Now, sensitivity analysis is used by economists a lot. It's a technique used to show the effects of changing one or more variables on the outcome. So typically you have a formula where the outcome of this formula is your variable of interest. Let's say it will be your break-even point or your profitability. And then this profitability or break-even point is dependent using a formula on a number of other input variables. And I think spreadsheet software such as Excel is the common and the most convenient way to implement that model. It will look something like this. So here you have, you plug in number about your sales, sales price per unit, meaning the price of your product, manufacturing cost, your fixed monthly expense, and then based on that you get a break-even point in terms of the unit number of units sold, how many units you need to sell to reach a break-even point where all of your fixed and variable costs are covered, and also the revenue at the break-even point. So that 75,000 will cover all of your expenses. And then the reason it's called sensitivity analysis is that you change one or two variables and you see how sensitive your outcome variable is to that change. So you will say, okay, let's say I want to decrease the price by $1. So instead of 12, you plug in 11, and then you'll see a totally different outcome here. So that's why it's called sensitivity analysis. You change the input variables and you see how you model, how sensitive your model in responding to those changes in underlying independent variables.